that's where I have this all written out right here, right? So I'll remind you, f of y we said was, or excuse me, psi of y was f of y e to the negative y squared divided by 2. So there that is, where I'm going to replace f of y with my Hermite polynomial in y. We've got there the e to the negative y squared divided by 2. And then finally, we've got a to be determined normalization constant that, as it turns out, is going to be also a function of quantum number nu. Okay, so now what I want to show you really quick here, this gets kind of confusing because here you see this is written as psi of x, but now we have this written as h of y, but now this is written as e to the negative y squared divided by 2. Okay, well, here's all of those constants that we collected, all right? And this is standard to give them in the 1/4 power. And the reason for that is because if we were to go and do a unit analysis on all of these constants, we would actually get that this alpha term is meters to the 4th power. So by taking the 1/4 root of it, we get units of meters. And then now check it out. Our y equals this x divided by alpha, where once again, that was a collection of all of those constants, okay? And so now when we see these functions in terms of y, our y scale becomes unitless. So we can kind of, and that y scale is still the displacement scale, right? I could still think of this displacement in terms of y. However, when we use that y, this distance is unitless and it is scaled by the alpha constant. However, if we wanted to actually do this in proper units, okay, then any place we see a y, we replace it with x divided by alpha, all right? And then we will actually be calculating the wave function in actual, units of displacement, okay, in terms of meters if we used, all of our standard notation. So for example, if I wanted to now continue writing this psi of x, okay, I'm still going to have this, to be determined normalization constant. But now when I rewrite my Hermite polynomial, I've got to rewrite it not as h of y, but rather h of x divided by alpha, okay? So over here, right in my Mathematica, I could replace that with, I'm just going to say x divided by a, okay? And yeah, I would have to do that in my polynomial because that's going to help me properly take into account all those units that we dropped out, okay? And then also, this is no longer going to be an e to the negative y squared divided by 2, okay? Rather, it's going to be an e to the negative x squared divided by 2 times alpha squared, all right? And now I can think of my wave function only in terms of x, which is convenient based on, that we always like to think of this scale as the x scale. Okay, and the last thing that I'm going to point out in this lecture, and I'm just kind of shortcutting. I'm not showing you that we get directly to the result for energy, right? But remember, we sought out to solve the Schrödinger equation Hamiltonian as a function of quantum number nu now, psi of nu, that equals E of nu times psi of nu. So here is our energy solution, which goes as E equals nu plus 1/2 times h bar omega. So it's a lowercase omega. And that's not operator omega, it's just the Greek letter omega. We don't have enough letters. So what is omega? Well, this is what we call the oscillator frequency. And that oscillator frequency is given by the square root of the force constant divided by the mass. And so what's really cool about this solution here, what I'm going to show you now, okay, what we predict in this model all of these different quantum numbers when we put them in there. So for example, the first one is 0. We still have an energy level that's at 1/2 h bar omega. Okay, well, what about if nu is equal to 1? Well, then that next level is at 3/2 h bar omega. Well, what if nu is equal to 2? Well, it's 5/2 h bar omega. And so what you'll notice here, as indicated by this picture, the energy spacings are linear, so they're the same as you go up, and they have values of h bar omega. Well, why is that cool? Well, remember back in your Gen Chem days, E equals h times nu, right? Which equals hc over lambda. Well, look at our solution. Our solution is h bar times omega, but that's still Planck's constant times frequency. Really, really cool that it comes out like that, okay? So our oscillator frequency, right, that's going to have units of 1/seconds. We know h bar has units of joules times seconds. So this is perfect. This is a really cool result. I think it is. Okay. So I've been talking for about 36 minutes, so I'll cut it off here. Coming up next, we're going to normalize this wave function and actually find out the normalization constant. Okay. And as you can also see from my Mathematica file, I've got calculations of alpha here, so where I'm actually going to show you what happens when we apply real numbers into this whole alpha thing and how it sets our scale for displacement. Okay, folks, I'll see you in the next video.